All right, let's go and take a look at another example. And really the key here is just to spend the time identifying what the pieces are. So here, if I want to match the form of a first order differential equation, now not all equations are first order linear, so you won't always be able to match this template, but sometimes you have to pick things apart a little bit. Like here I see y over t and not something times y. But if what I do is I just go ahead and separate the y over t as 1 over t times y, now you can see that the a of t is just the 1 over t. And here I have plus 3, and so I can identify my parts again as 1 over t and 3. So first step, take the time to do this, because if you don't, it's easy to make a mistake. So step 1, let's go ahead and get mu, which is e to the negative integral of a of t dt. Now, a of t is the integral of 1 over t dt. And here's the thing, we'll enter this into Wolfram Alpha just to show that it'll simplify it for you, but the integral of 1 over t is the natural log of t. And so what you'll end up with here is e to the negative natural log of t. Here's the problem with this statement. The problem here is that this e to the negative natural log of t, we can't actually just cancel out the natural logs and make this e to the negative t. What we have to do is use the property of exponents of logarithms that says that since there's a -1 coefficient out here, -1 times the natural log of t is the same thing as the natural log of the argument of natural log to the -1 power. So it's this rule where when you take the natural log of something, you can bring the power down, but you can also bring it back up. So when you do integrate this, this comes out to, now the natural logs cancel, and you're left with t to the -1, which is the same thing as 1 over t. Sorry, this is equal to mu. So if we integrate e to the negative integral of 1 over t dt, that should reduce it down for us to what we calculated, which is 1 over t. Great, and so we have mu. Now we're ready to take care of step 2, which is to find the general solution. This is going to be y equals 1 over mu, so 1 over mu times the integral of mu times b dt. Okay, and so now we can substitute in mu, which is 1 over t times the integral of 1 over t times b, which is 3. And this is dt. I'm not sure what happened over here. All right, so we can compute that integral. This is not a really difficult one to compute if you wanted to do it by hand, but just to emphasize that there's a faster way, integral of 1 over t times 3 dt. And what we'll find is it comes out to 3 natural log of t plus our arbitrary constant. So that's the critical part here, is that we have to remember that this whole expression here comes out to 3 natural log of t plus our arbitrary constant. So this coefficient here, it's 1 over t. So multiplying 1 by the reciprocal of 1 over t will leave us with t over 1. And so now we distribute that in, we'll get 3t natural log of t. Be careful, the t cannot go into the natural log. And then plus ct over here. Great, so there's our general solution. Now step 3 is to take care of our initial condition. So if we plug in our initial condition that at time 0, y is 10, we get 3 times 0. I'm gonna adjust this just a little bit here. My initial condition of y of 0 equals 10 is not going to work because the natural log of 0 is undefined. So actually what would happen in that case is this particular function does not have a solution for that initial condition, or at least not using this method. So let's just change the initial condition to y of 1 equals 10. This is actually called a boundary value, boundary condition problem. So we'll have 3 times 1 times the natural log of 1 plus c times 1. And to solve this, we just have to say c equals 3 natural log of 1. You can approximate that if you'd like. I'll just go ahead and substitute it into our equation up here. So y equals 3t times the natural log of t plus 3 natural log of 1 times t. And there is our particular solution. Nice. Okay, so now we have solved our second differential equation with this.